Hello and welcome to 4.1 Related Rates. In this section we're going to be looking at a series of word problems where we compute the rate of change of one quantity in terms of the rate of change of another quantity. So this involves taking the derivative and using the chain rule with respect to time. Okay, so let's take a look at how we can set up some of these problems. Inflating a balloon. Air is pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So one of the things we want to make note of is here in the problem. It says the volume increases at a rate of 100 centimeters cubed per second. Okay, so whenever we see the word rate, that's going to be a derivative. Okay, so if it's volume increasing, okay, and it's a rate of volume, we will say this will be dV dt. And that's going to be 100 cubic centimeters per second. How fast is the radius of the balloon increasing? So now how fast is the radius increasing? That's another rate. So that's going to be dr dt. Yeah, that's what we'll be looking for when the diameter is 50. So d is 50. Now if the diameter is 50, we take half of that to get the radius, which will be 25. So now we need to have the formula that connects all of this. Okay, we recognize that it's a spherical balloon. Okay, so if it's spherical, we could use the formula for a sphere, for volume of a sphere. Now volume of a sphere is V equals 4/3 pi r cubed. Okay, so if we take this formula and then if we differentiate with respect to time, okay, that will give us, so let's take the derivative, that would give us dV dt equals 4/3 pi. Now the derivative of the right side, the 3 will multiply in front, and reduce the power, and then multiply by dr dt. So you're using chain rule throughout the whole process. Okay, we're differentiating with respect to time. So each of these variables, the v and the r, will have the chain rule piece attached to it. Okay. So now when we simplify this, we have dV dt equals 4 pi r squared dr dt. Okay, and now we could plug in our knowns and then we could look for our unknown. Okay, so our unknown is dr dt. We know dV dt is 100. We know that r is 25. Okay, so let's plug those in. So we have 100 equals 4 pi 25 squared dr dt. That's 4 times 2500 times 25 is 2500. So we have 2500 pi dr dt equals 100. Okay, we could divide both sides by 2500 pi. Okay, so that leaves us with dr dt equals, we could reduce by 100, so we would have 1 over 25 pi, and that would be centimeters per second. Okay, and if we put that into a calculator, that would be approximately 0.0127 centimeters per second. Okay, let's take a look at another example. The sliding ladder problem. A ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Okay, so I like to draw a picture with this. I got my wall, the ground, we got the ladder. Okay, so it's a 10-foot ladder. Okay, we got the ground, the wall. Okay, so we would say that this is going to be x feet away from the wall, and then how high up on the wall would be y feet. Okay, so now it's set up in terms of a right triangle. Okay, and when we think right triangle, the Pythagorean theorem comes to mind, especially when we're dealing with the sides. Okay, so the way we would set up the formula would be x squared plus y squared would equal 10 squared. So now what we do know is that the bottom of the ladder is sliding away from the wall at a rate of 1 foot per second. Okay, so it's sliding away from the wall, so that's going to give us a rate of the x. So we know that dx dt equals 1. And then we want to know how fast is the top of the ladder sliding down the wall. So how fast is y changing? So we're looking for dy dt when the bottom of the ladder is 6 feet from the wall. And we also know that the bottom of the ladder, x, equals 6. Okay, well, 10 squared is 100. And so the equation, when we differentiate, will look like this. Just take the power rule. Derivative of x squared is 2x times dx dt plus 2y dy dt, and then derivative of 100, which is a constant, equals 0. Okay, so we're looking for dy dt. We have x, we have dx dt. Now, when x is 6, we can figure out what y is, right? So just putting into the Pythagorean theorem, 6 squared plus y squared equals 10 squared. Okay, so we have 36 plus y squared equals 100. Subtract 36, so y squared equals 64. So y equals 8. Okay, so now let's plug in. we have 2 times x, which is 6, dx dt, which is 1, plus 2 times 8, right, y is 8, dy dt equals 0. Okay, so we have here 2 times 6, that's 12, times 1 is 12, plus 2 times 8 is 16, dy dt. Okay, and then we're going to subtract 12, so we have 16 dy dt equals negative 12. Divide by 16, dy dt equals negative 12 over 16. Reduce. So that gives us negative 3/4. Okay, and so that would be negative 3/4 feet per second. And that would be it. Okay, so the ladder would be going down, okay, and the negative implies going down 3/4 of a foot every second. Okay, let's take a look at this one. Filling a tank. A water tank has the shape of an inverted circular cone with base radius of 2 meters and a height of 4 meters. Okay, so radius equals 2, height equals 4. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which water level is rising when the water is 3 meters deep. Okay, so water is being pumped into the tank at a rate of 2 cubic meters per minute. So that's a rate of volume, right? The volume is growing by 2 cubic meters per minute. So dV dt is equal to 2. Find the rate at which the water level is rising. Okay, so we need to do that. Find the rate at which the water level is rising. So that's going to be dH dt. That's what we're looking for. When the water is 3 meters deep. So when h equals 3. Now the formula for volume of a circular cone, okay, would be volume equals 1/3 pi r squared h. Okay, so it's the old formula for the volume of a cylinder times 1/3. Now one of the problems with this formula is we have r squared and h, and there's going to be like a product rule situation there. Okay, and that's going to get a little complicated. So in order to simplify things, we're going to tie in the r with the h, so that maybe we could write this in terms of either r, all r's, or all h's. Okay, so the one way we do that is we make the relationship between r and h. Okay, use like a similar figures model. Okay, the ratio of r to h, r over h, is going to be equal to the ratio of 2 to 4. Okay, and if we solve this for r, okay, what I want to do is solve this for r in terms of h, and then I could replace r with h, and I have my formula all in terms of h, because I'm looking for dH dt when h is 3. So it would be easier if the whole equation was in terms of h's instead of r's. Okay, so if I have r in terms of h, that would mean here I have 2h equals 4r. Right, if I do my cross multiply property, and solving for r, if I divide by 4, r would equal h over 2. Okay, so now let's replace r with h over 2. So I have v equals 1/3 pi h over 2 squared times h, which equals 1/3 pi h squared over 4 times h. Which means if I have a denominator 4 and a 1/3, that means I have v equals, I can multiply those two and get 1/12 pi h squared times h would be h cubed. Okay, so now I could take the derivative of both sides. So I have dv dt equals, a power rule, 3 times 1/12 times pi reduced to power by 1 times dh dt. Okay, 3 times 1/12, that's 3/12, so 1/4 pi h squared dh dt. Okay, so now we have our formula, dv dt equals 1/4 pi h squared dh dt. And now we're ready to plug in. Right, dv dt is 2, h is 3, and we're looking for dh dt. Okay, so plug in. dv dt is 2, h is 3, okay, so that means we have 3 squared is 9, 1/4 times 9, that's 9/4, so we have 9 pi over 4 dh dt. And then to solve this for dh dt, we can multiply by the reciprocal of 9 pi over 4. Okay, so that ends up giving us dh dt equals 4 times 2 is 8, 8 over 9 pi meters per minute. Okay, and that equates to about 0.28 meters per minute. So some of the strategies involved in solving these related rates problems. Okay, you want to read the problem carefully, draw a diagram if possible, introduce your notation, right? You want to identify what's given, right? And what is being sought out, what's the required rate. Then you want to write an equation that connects everything. Okay? In the last problem you saw we eliminated one of the variables by substitution. Right? So we solved r in terms of h. Okay, and we kept it simple in terms of one variable. And then we use the chain rule when we take the derivative of both sides with respect to t. Okay, and then we use the given information, substitute in, and then we solve for the unknown rate. Okay, let's take a look at example 4. Car A is traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour. Both are headed for the intersection of the two roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? Okay, so let's draw a diagram for that. Okay, so car A is traveling west. So let's say here's A, it's traveling west. $50 miles per hour. Car B is traveling north. Okay, here's B. Traveling north. Both are headed for the intersection. Okay, so here's the intersection of the two roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? Okay, so what's connecting them would be this, right? So we have another right triangle situation. Okay, let's call this x because that's the horizontal direction. We'll call this y, that's the vertical direction. And let's call this one z since we have x and y. So now what's going to connect all these is the Pythagorean Theorem. Right? X squared plus y squared equals z squared. Now one of the things we're going to note here is that we have at what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection. Okay, so we know that x is going to equal 0.3 and y is going to equal 0.4. Now we're also given dx dt and dy dt. Okay, now the only thing with dx dt and dy dt, they're giving us 50, for example, for car A. Right? Now that's actually going to be a negative 50. And you might ask why? Why is it negative? And the reason is because that the distance of A to the intersection is shrinking. Okay, so because that distance is shrinking, it's going to make sense that the derivative is also going to be shrinking. So it's got to be a negative. Okay. And so if we look at the dy dt, similar idea. Okay, because its distance to the intersection is also shrinking, we would say that its rate is also negative. Should be a t. So we have dy dt is negative 60 miles per hour. Okay, so now, and then what are we looking for? We're looking for at what rate are the cars approaching each other. Okay, so that'll be dz dt. Right, we're looking for dz dt. Okay, so let's take the derivative of our equation that ties everything together. Okay, so when we take the derivative of x squared, we would get 2x dx dt plus derivative of y squared is 2y dy dt, and then the derivative of z squared is 2z dz dt. Okay, and now we could plug in, right? Plug in our values. Keep in mind we're solving for dz dt. So we have x, what was x again? 0.3, y is 0.4. Okay, so we have 2 times 0.3 dx dt is negative, what was it, 50? And then 2 times y was 0.4, dy dt, which is negative 60, equals 2 times z. Now, we don't have z, but we could easily figure it out because we have x and y, and it's a Pythagorean theorem. Okay, and it also fits a 3, 4, 5 pattern, right? So 3, 4, 5 is a Pythagorean triple. So 0.3, 0.4, z would be 0.5. And then we're looking for dz dt. Okay, so now multiply these together. Okay, we have 0.3 times negative 50, so that'll be 5 times 3, 15, negative 15 times 2, negative 30, plus 4 times 6, that's 24, negative 24, that's negative 48. 2 times 0.5 is 1, so 1 times dz dt is dz dt. And negative 40 plus negative 30 plus negative 48 is negative 78 is equal to dz dt. So what does that mean? That's miles per hour. Okay, so that means basically that the two cars are approaching each other at a rate of 75 miles per hour. Okay, they're getting closer because of the negative. Okay, if this had turned out to be positive, that would have implied they're getting farther away by 78 miles per hour. But because it's negative, this means the two cars are getting closer by 78 miles per hour. Okay, let's take a look at our next example. A man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? Okay, so let's draw a picture for this. Man walks along a straight path. Okay, so let's call this the straight path. We'll call it X. And we have a searchlight is located on the ground 20 feet from the path. Okay, so we have 20 feet. Okay, here we have a searchlight. Okay, so we got a right triangle. Okay, so the searchlight is 20 feet. It's on the ground 20 feet from the path and is kept focused on the man. Okay, so it's shining towards the man. At what rate is the searchlight rotating? So we're looking at an angle here. When the man is 15 feet from the point on the path closest to the searchlight. Okay, so this distance is going to be 15. So, and this is the path, this is the point. On the path closest to the searchlight. Okay, so we know that X is 15. So X is 15. This is 20. And then we have the man walking along the straight path, speed of 4 feet per second. So that's going to be dx dt. Now if this is a right triangle and we have 15, 20, the hypotenuse here would be 25. So now what would be an equation that relates all of this? Well, let's see, if we have the original setup with the X and the 20, and we're looking at this angle, right, and think about what we're trying to find. It's saying at what rate is the searchlight rotating? Okay, so at what rate is the searchlight rotating? That means we're looking for d theta dt, because that'll give us the rate at which this angle is rotating. Okay, so a simple equation that ties all this together and involving the angle would be, we have X, we have 20. According to this angle, we have an opposite and an adjacent. Okay, so we would have opposite and adjacent, that's tangent. So tangent of theta equals X over 20. So in other words, if we multiplied both sides by 20, we would get X equals 20 times tangent of theta. So when we differentiate this, we would have dx dt equals 20. Now derivative of tangent is secant squared theta times d theta dt. Okay, so now if we're going to solve this, well, let's solve it for d theta dt first. That's what we're looking for. Okay, so we have dx dt equals 20. Now secant squared is the same as 1 over cosine squared theta, d theta dt. In fact, we could just plug in. We know dx dt is 4. We have 20. For cosine squared, let's figure out cosine of theta. Okay, cosine of theta would be adjacent over hypotenuse. Okay, so cosine would be 20 over 25, which will reduce to 4/5. And so we would have 1 over 4/5 squared d theta dt. Okay, so if I simplify this a little further, 4/5 squared would be 16/25 d theta dt. Now 1 over 16/25, okay, 1 divided by a fraction is the same as multiplying by its reciprocal. Okay, the old keep, change, flip. So this gives us 25 over 16. Okay, and let's reduce a little bit to make this a little easier for ourselves. Divide by 4, and divide by 4, we get 5. So we have 4 equals 125 over 4 d theta dt. Okay, and then multiply both sides by 4 over 125. So we have 16 over 125 equals d theta dt. Okay, and that would be it. So if you put that in a calculator, that would be approximately 0.128 radians per second. And that would be the final answer. Okay, so any questions with this stuff, just email me. Okay, we'll see you in class. Have a good day. Have a good night. We'll see you soon.